Here L is defined to be the maximum value of the derivative of a function f which is given in the problem, and this function f is defined over the closed interval 0, 1. Also, here we have to look at the iteration method which is given by also the problem says that the function f is defined in such a way that on the closed interval 0, 1 there exists a unique point x star which is given in such a way that x asterisk equals f of x asterisk, and this is the only point in the domain of this function f which satisfies this such a relation. So now we need to check the given four options. Here option number 1 says so option number 1 says if capital L is less than 1, then the sequence of the approximations or iterations xn converges to the value x asterisk. This option is necessarily true, for from a theorem we know that the iteration method xn plus 1 is equal to f of xn converges always whenever magnitude of the derivative of the function f is less than 1. Therefore option number 1 is true. Now option number 2 says xn converges to x asterisk if L is greater than equal to 1. Let us take a particular example and we set f of x equals sin x. Now we know that sin x is a function which is twice continuously differentiable. Also over the closed interval 0, 1 this function possesses a unique fixed point which is 0, that is 0. Now we use this function sin x and then we find out that maximum of this function derivative over, and this will be easily seen that it equals 1 and it is equal to L. But now from the iteration scheme we can write Now we can see, since 0 is the fixed point, therefore 0 will be a solution for this scheme. And now say if the error in iteration of that fixed point is epsilon n in nth iteration, then we can write it now expanding this, we obtain for we can take epsilon n to be very small, and therefore we can neglect to all these higher power terms, and then we are left with, therefore now we obtain epsilon n plus 1 approximates epsilon n, which simply shows that even if n becomes sufficiently large, but still the error equals to the previously obtained errors, and therefore the sequence of the points xn can never converge to the fixed point 0, and therefore option number 2 is not true. Now we look at option number 3. And option number 3 says the error en equals xn minus x star satisfies the relation given as mod en plus 1 is less than L into mod en. So now from iteration scheme again we can write now we can write, since x asterisk is the fixed point, so n plus 1th iteration can be written as x asterisk plus n plus 1th error. The same way we can write on here now. Since en is very small, we can expand this expression by using Taylor's theorem, and then we obtain now, since at x asterisk f of x asterisk equals x asterisk, therefore these two terms are cancelled, and now we are left with also here we have neglected all other terms which involve higher powers of this error en, and therefore we obtain where L is the maximum value of the derivative of function f over closed interval 0, 1 as given in the problem. Therefore option number 3 is true. Option number 4 says if the first order derivative of the function f at the fixed point x asterisk equals 0, then modulus of en plus 1 is less than c into modulus of en square for some real number c which is greater than 0. Again, from the above representation we can expand f of x asterisk plus en by Taylor's theorem, and then we obtain an expression of this form. So we write this line again. But now again x asterisk is the fixed point, therefore f of x asterisk and x asterisk are cancelled. Also at this moment we have f dash of x asterisk to be equal to 0, therefore this second term also vanishes. Now we have this third term on the right hand side as the governing term, so we can write this time again we have neglected all those terms which involve powers of this error term en which are 3 or higher. Now let us take any positive real number c such that then we can write this expression as therefore option number 4 is also true. So we have option number 1, option number 3 and option number 4 to be true.